And welcome to this first session of a short training on Linux cybersecurity. We are going to talk in this sixth session of roughly 1 hour each, with an expectation of homework between each session of likely, I would say, 2 to 3 hours. We will take you through the different mechanisms which are available in Linux in standard to protect Linux services from cyber attack. Like any training, it doesn't have the pretension to see everything or even to go in every single detail. Far from that, but we hope that at the end of this set of sessions, you will have a better understanding of which tools are available and what they can offer you as services in order to protect your own systems, and will give you the desire to go a little bit further in order to unfortunately work on these today required protections. So I am Dominique Arfol. I actually work for Intel, a company doing chipsets. I am working from my home in Brittany in the west of France, by the seaside. And I've been dealing with cybersecurity for quite a long time, until that for Linux as well. I did my first project on Linux, started roughly around 86, 87. At the time, to be honest, security was not a problem at all. And I did have my first real serious problematic of security when we deployed in British Telecom a system which had the capability to cut every single telephone line in the country. Then we started really to look at, protecting system and what was available. Unfortunately, Linux has been used a lot in services which are heavily facing the bad, dark internet, especially through web servers, and furthermore with implementation of financial transaction system, especially for very fast trading, which most of them runs on Linux, where really protection became something absolutely standard. So we've been pretty lucky in that way that a lot of very interesting and financially critical projects were requiring features which then have been implemented. So we'll have a look at that. If you have any questions, you have my open source public mailing list. I will hand reply to questions which make sense or are not obvious to find. If I have opportunity to help, I will. Now I also have a professional life, and I am not always available currently for information. I'm just working on automotive grade Linux, or AGL in short, and before that I've worked on different operating systems, at least in my recent past professional life, such as Tizen or Amigo, if we go a little bit further on. So let's go to the next page. It's always a problem to go to the first time to the next page, but we'll succeed it. So I expect that before really being able to do any of the homework I will give you, will have to do a few basic things, and don't expect that by just watching a few videos you're going to be knowledgeable. Hackers are extremely professional, they are extremely skilled, and so you will have to be skilled as well. A lot of people in charge of cybersecurity consider that the admin is the one who is skilled in admin. That is a wrong assumption. Admin are very good at doing what is expected to be done, and likely they will always be better than you at that. But they are rarely trained to go into the unexpected. and they are also very trained to be completely paranoid. So that's going to be your job, and for that you have to get a bit of knowledge. At least you need to know what can be done and have a clue on how that can be done. So when you will ask to the IT guy in your company or the admin team, depending on the size, to implement a feature that you really need, they cannot bullshit you out. So you will have to get your hand dirty. If you don't do that, you will likely never be very good at real implementation of cybersecurity. So I expect that you will have implemented CentOS on a virtual machine. Why CentOS? Very simply because it's de facto a copy, open source copy of Red Hat, and Red Hat is the most used distribution in the professional world. It's very basic, so it's a very professional approach. Now, is that the only distribution? No, by far not. Personally, I always use OpenSUSE. And SUSE also has professional distributions, and Ubuntu is also popular, or even Arch if you really want to understand how distribution is done. But this course will assume CentOS. Now, you could do it with other distro, but it's just going to be more difficult. So I will expect that you have it running on a VM, and that you will activate base boot based on UEFI rather than the traditional BIOS MRB or master boot record. So you will have to install the repo, create a user, and I would like you to install a web server which at least can respond to a very basic HTML.index page, just to say that it's live. To be honest, if you install the web servers, which is provided on the repo with CentOS, you will have this test page. And that for the time being will be enough, so it's really very basic work. So what are we going to see in lesson 1? We're going to look a little bit at the Linux boot process, then how systemd takes over from that, and then we'll look at a few basic things on the protection side, like the discretionary access control, so UID and GUID, a little bit of how sudo work, which allow you to escalate your privileges for a bit of time and get an introduction on extended access control, and I will propose you a workshop. So this is a course which has been designed for an engineering school in Van in Brittany, dedicated to cybersecurity, and people have workshop. Now, this is on the internet, you do whatever you want, but if you don't do the workshop, you will never be at the level that you should be if you have a real job which requires a real knowledge in cybersecurity. So why the boot process is so important? Because anything which happens before that Linux works is going to be invisible from Linux, and that's a very important point. So anything that will be installed under the operating system is not visible by the operating system. And actually quite a lot of things can be installed before the operating system and will run under the operating system. If you have implemented CentOS as a virtual machine, as I asked you to do, actually you have a hypervisor running in your host, which is running your virtual machine as a guest. So that host has capability to do things that your guest doesn't say. And it can actually affect the guest very seriously. So what is a boot process? The first part, we have a BIOS. At least on PCs, we have a BIOS. It's not true on embedded devices, which mostly are based on ARM architecture, but on servers and PC, the BIOS is very important. The BIOS is actually providing two features. The first one, it does initialize the hardware when you do the reset. But also it provides you tables that you may have noticed called ACPI, formal descriptions of the hardware, and that allow you to run operating system on hardware which were not known at the time the operating system was actually built, which allow you to run binary images. This is why you can run Windows on fairly old PCs. And Linux as well, while you just download them from the internet. So you have no knowledge of your exact hardware architecture, but it's still boot. So the BIOS does that job for you. UEFI is an extension that was originally designed to allow very fast boot for Macintosh when Macintosh decided to use Intel chipset. It's a small operating system. It also allows to implement secure boot, which is required if you want to boot Windows 10, for example. So most of PC have it by default. Can also boot Linux, but it can do a lot of more things than that. UEFI is a pretty sophisticated piece of kit. And traditionally, it's an Intel hardware. You will have Grub as a secondary bootloader, and systemd boot will be the third level of boot. So you will have first UEFI, then Grub, and you know, as alternative to Grub, you could have systemd boot. So you have two alternatives there. Systemd boot is one way faster, but a bit less flexible. So a lot of distribution stick to Grub, which allow to do very sophisticated things, especially when it comes to select automatically snapshot going backward, which is very handy when you had a problem. But Grub 2 has a GPL-v3 license, which, for example, in embedded devices is a real problem. It's not a problem on PC. On ARM architecture, most of the time you will have just a very basic U-boot, which is doing the basic hardware initialization, and then will go to the secondary level and boot a kernel, and that kernel will have a device tree which will give a description of the hardware. So it's a very different concept. So you cannot most of the time run on an ARM an operating system that is being downloaded on the binary. It has to be downloaded for that specific hardware. And after that you have a kernel, and the kernel will have an Init RD, and Init RD will allow to mount a minimum system that will start systemd, and systemd will boot the user space daemons, and when you're ready for graphic, you will have a login manager coming, assuming you have graphic. You can still have a login manager even in text mode. So what we see out of that is a lot of things happening before that actually you can start to type a simple stupid command as ls on your terminal. So let's have a little bit of a look more inside. So the initializations, and I will only talk about PCs because it's what most of you will have to deal with. This says, you know, if you are in charge of cybersecurity in a company, a lot of embedded devices are running Linux and can be pretty dangerous. The most common one, most known one for being hacked, have been the surveillance camera. But don't misunderstand, you know, you also have other devices. For example, all the connected TV are running Linux, as a matter of, you know, statistics. It might have a few exceptions, but fundamentally they are Linux boxes. And a lot of the devices you have on the network are also running Linux. So you have a lot of other things, and those are embedded devices, so they don't boot like PCs, and they don't have the same way to be weak on that area. So don't ignore them. But on a PC, so you initialize the hardware, you have a basic configuration, you can give boot order and restrictions, and it will validate the level 2 boot, assuming you didn't deactivate the secure boot feature. So what that means? That means that the secondary boot level has to be signed by an authority which has a valid certificate in the UEFI BIOS, so in the flash of the device. This certificate are actually by default from UEFI from Microsoft. Microsoft, even if UEFI is an open source project from the API point of view and specifications, only Microsoft took the burden to actually do that job because they needed it for Windows. So you have to get, if you want to write your own bootloader like Grub and you want to work with secure boot, you have to sign your stuff with Microsoft. So you have to get a key which is, you know, signed by Microsoft. That's option 1. Option 2, you can actually change the keys inside the UEFI BIOS. That's possible. You can put your own keys, and that could be a very valid strategy if you have very strong requirement for security. and it will validate your boot level 2. Now your boot level 2, for example Grub, will load the Linux kernel. Now by default Grub does not verify any signature on your kernel. And actually the distribution like Red Hat or SUSE, even the professional one, do not ship you signed kernel. So if you use the standard upgrade mechanism from Red Hat or from SUSE, you will not have signed kernel. So that's a point that you have to be very careful. Do you need to have a signed kernel at that stage? In some cases, yes. It would definitely avoid to load something you don't want to be loaded. And it's not easy to actually go around that. But more importantly is the boot, because the bootloader, that one you want to really get signed, because the bootloader would have the capability to launch, if it would have been attacked, under your nose a hypervisor that would be running under your Linux machine. And one thing that is a weakness of the UEFI is that UEFI reads all its configuration file from a dedicated partition, which is called a GPT partition, but practically that is a FAT32 file system, and FAT32 cannot provide you any protection, which means that it is pretty easy if you have physical access to a machine to actually implement something that will be running under Linux, and then you will not know it. So it's a very critical point that you need to know. And it means that if a malicious code is capable at any time to get on your system and start to play with this mount point, which is the UEFI mount point, it will have capability to write on it, because as a FAT system, it's visible by all. Now, there are a few tricks that you can do that definitely needs to be done if you want to protect. When you mount a file system in Linux, which has no protection, you can actually decide to allocate it to a given user and to put specific write on it. So a good strategy is when you mount, in order to allow the upgrade mechanism of your distribution to work, the UEFI partition, traditionally it's mounted in /boot/EFI, is to mount it as a read-write, because you need for update, but to mount it with restricted write, so only root has capability to read and write on that partition. No one else has any need to get in that partition. So there is no reason not to do it like that. And that's a pretty simple, reasonable level partition control. Now, once you have really passed the BIOS, UEFI is going to load a binary. And that binary, as I've said, is either going to be Grub or is going to be systemd boot on a PC. Practically on the distribution, it's most likely going to be Grub2. And as I've said, the reason is that Grub2 is significantly more capable to do things. And in particular, you can implement plugins, and those plugins, for example, can have capability to take snapshots of your hard drive. So if your file system is BTRFS, when you do upgrade, it will do snapshot automatically. And so if you have a problem, you can go backward, which is very, very handy. So that's the second level. It will actually be signed by default if you have a big distribution, so you can activate secure boot. The Grub2 binary is signed with a proper key. So if someone changes it, you will know. Now, changing the Grub is one point, that's signed, but what is not signed is what is going to be loaded by Grub, the configuration file, all that, nothing of that is signed. Which is why you have to make it in a partition, as I've said before, which is only accessible by root, which required a specific option in the mount point, which normally is not done in standard by distribution, in order to restrict that to root. And they are very capable. They can load non-signed kernel. Actually, they are loading all the time non-signed kernel. Now, you could make a specific plugin to load only signed kernel, but then you will have to manage your upgrade process by yourself, which, if you are running in a critical business, is certainly something you want to do. It can execute plugins, and it has a huge flexibility in configuration. System deboot is very similar, but it's less flexible, which can be good and bad, But typically, when it comes to have a very nice UI allowing you to load a snapshot from yesterday because your system doesn't work anymore with something that happened today, it's not as nice. But otherwise, it's pretty equivalent. And this is an example you can see on the graphic where you can have some different functions, and for example, you can load a rescue CentOS system. Now, once you have that, you're going to have Grub or systemd to load the kernel, load the Init RD, we'll come back to that very quickly, and to trigger the return, the kernel. So the kernel command line is going to give quite a few informations. First, obviously, you're going to say, well, is a kernel, which is just simply a binary file. Where is Init RD? The Init RD is a file that will contain, in general, two things on a PC. It's a CPIO archive by default. The first part of the CPIO archive can or cannot be, that's optional, be microcode to upgrade the firmware of the CPU. If you have a modern distribution, that's always going to be the case. You will have the Intel firmware upgrade there, which can upgrade a few features in the SOC. And then you have another behind that CPU archive. You will typically have T files. So the first is the binary firmware for the chipset himself, and the second part is an image of a file system. Traditionally, that image of the file system was also a CPIO archive, and today, because of mandatory access control requirement, it's not uncommon to see it in a different format, which is ext4 most of the time, in order to be able to carry mandatory access. And finally, new kernels are capable to have the Init RD format not in CPIO, but to have it in gzip CPIO. So in the zip CPIO. So it's important, if you want to look into an Init RD, to use a file command to really peel it, with the right command, because it can be in different format. What will you try in Init RD? Init RD is the initial image of the root file system. In Linux, like in all Unix, everything is a file, and a file has to be in a tree. There is only one tree. There is no concept of device letter like you had on DOS and later on Windows with A, B, and semicolon. No, that doesn't exist. You just start with slash, and then you have just a tree. And you can mount different devices in different places in that tree. Everything looks like file. So the Init RD is the initial source of the tree, and it can have a few directories, and it will contain what is needed to actually start to mount the complete file system, which quite often include things such as the file system modules for reading, more sophisticated file system, which may not be in the kernel because it takes too much space. You can have some drivers to read some peripheral that are not in the kernel. For example, if you are booting from a network, you can have the network interface because you have plenty of different network interfaces and you don't want to have them all in the kernel. So you will have a few things, but you will also have utilities because you're going to need things to do the next step. First is typically you need a utility to check that the file format of the system you're going to mount as the next step are valid. So you want to check them. Before mounting them in read-write, you want to make a quick check file system. So this type of things is going to be located in Init RD. Why I talk about Init RD with such intent in a training on cybersecurity? Because in Init RD you're going to do very early actions, and you could do action at that level which are so low that it would be very difficult to see them after inside your running Linux system. When you boot the kernel, it will actually start a process called init, which always has a PID 0, and init will start to execute things in Init RD. So if you put things at that level, it's going to be very, very low in the system, which means that it could potentially activate, hide itself, and wait for the good time to come back. And it will be very, very difficult to detect, because the Init RD, when you look at it, you don't really know easily what is inside. I've said before that it's actually a pile of a two-level archive, compressed often, so it's not something you see easily inside what is in. So it's a good place to hide very low-level malicious code that will be sleeping until the good time to come is there. And so you have then on this kernel line, which is on the launched by the secondary boot, you also have a number of options. You can change a lot of things. In particular, you can deactivate the mandatory access control. You can boot with security called none, even if you had SLinux or SMAC or AppArmor actually activated on your system. So capability to go and change that is critical from a cybersecurity point of view. Is it common? No. Does it require physical access to the machine? Not entirely. Definitely easier if you have physical access, but you could do it in a remote way as well. So it's not something very difficult to control, but don't forget that. So we talked a little bit about the Init RAMFS. So this is just a graphic explaining what you have inside. So Init RD is quite often called Init RAMFS because originally in the Init RD you had just the initial script, and then we started to put a minimum file system in it, and then we had to, firmware for the chipset. So people tend to use one word for the other. Technically, Init RD is a file which is loaded and given to the kernel, and it can include more than just a file system image. And inside you will have, as I've said, a few firmware, a few drivers, and a few utilities and command of what you want to execute next. Have a look at one, look at how it's done. It's a good exercise, because it's something, if you don't understand how a system is infected, that you may want to look. It's quite quickly done, but you need to know how to do it, or at least to remember that it can be done, so you can ask to someone who is technically more hand-ons to do the verification for you. Once a very basic part of the system, so the kernel is probably the first thing is going to start. It's very quickly systemd, and it used to be Init RD, where the name's Init RD, but it was called a system called Init Tab that was started an RC system. They are still used in the old system, and I will not talk about it. Fundamentally, it was doing a little bit the equivalent, just systemd is significantly more efficient in parallelizing things, so we can do things in parallel, which is very practical. Sorry, my socket is going down. And so systemd is used in all new system, including very conservative people like Debian have switched to systemd a few years ago. Systemd starts services by dependencies. It can also start them on request, on need, if you want. So, for example, on detections of a socket, or request on a socket, or on the dbus, it can be on a wait on some event like that. It manages log. It's not simple at all, but it is powerful. It's based on a very complex set of symlink which are created by the command line, and you can get very, very quickly lost into systemd. Now, if you will have one day to troubleshoot what's happening in the system when you have been attacked by a malicious code or activities, you really need to know your base command. You need to really know how to use system control, check the services which are running, check the services which are not running but loaded and waiting, which triggers them, what could trigger them. You need to be able to read that, and how to use a journal command. Actually, the journal command is pretty handy, and in one way significantly easier than when we had a traditional system log. Now, systemd can start services as normal system, but it can also start them as user. Since the version 2.35, it can even start them inside a user session, which means that it can actually set variable for that, which means that the way the command is executed when started by systemd may be very different than the way when you start by yourself by hand. So it's not an area you can ignore to understand how it works, and more what it can do and it cannot do. So you have the capability to understand what's going on. Have a look, play with the systemd control command, and look at how it's done. Check the link, check how it's done, check how a unit is done and how it's created. You need to understand that, and it will take you a bit of time, I'm afraid. And as the image is showing, it can do a lot of things, and sometimes can make a few crack. Now, we could think, yes, great, now we have booted the system, now our kernel is running, the system daemon have been started by systemd, we're good. No, we still have the display session manager. And I took an example of a graphical, actually a pretty old one, which requires a login. We will have seen that. No, and it can be in text mode, say. What a lot of people forget is that actually the session manager has the capability to start daemon in the background for the user. Now, the fact that they are started with the user privileges in one way is reassuring, because system privileges, if people are reasonable, are pretty limited. But the bad side is, because these configuration files are designed to be modified by the user, it means as well that they are writable most of the time by the user. Which means that if you have a malicious code which is executing, for example, inside an app like a browser, it would have the capability to change those files. And then you would restart malicious code every time you log without knowing it. Now, is it visible if you go with a system PS? Yes. You can list status, you can look what it does. Are most of people capable to understand that? No. So it's definitely not as powerful that if you would hide a piece of code starting under Linux inside the secondary bootloader, but it is very easy to do, and it still can do a lot of things. Especially it can listen and grab every activity done by the user. So if you want to collect information, it's a very powerful point. It's a very interesting place to be. So once, if you have problems, sometimes it's quite worth to look at that and look at what is started in the background by the user every time it connects. And some of this display manager, like KVM or GDM, KVM is KDM, not KVM, sorry for the typo, are pretty powerful, and they actually are capable to start things even on demand, so waiting on dbus, for example, on some socket. So they can do a lot of things, and sometimes they can do things that you would not like them to be able to do. Now, what do we have to protect ourselves? So now we have seen more or less the different places where in a common Linux implementation there is capability to start code under an indirect control of the user, of the admin, in such a way that actually more or less they will not see it. Now, the first level of defense you have is to use the UID and GUID, so the user identification and group user. The group identification is not GUID, it's GID, sorry for typo, should not be the U. Those are always there. I told you already that we can use them when you make a mount of the file system which contains the UEFI boot configuration, you could make that to only allow super user to get access to it, which is the UID 0. A UID can have multiple group ID. That's absolutely perfectable, capable to do. And by conventions, everything is read, write, execute. On a directory, the concept of executing is the capability to read that directory. Now, that's basic. Now you have the ACL. The ACL allows you to provide a system where you are going to have multiple users to have write on a given file, which by default is not available. But if you have a file system which has extended file attribute, which is most of the modern one, you will be able to do that, which allows to have two or more or less two equivalent owner of a file, which can be very handy. One of the disadvantages of that, you will see very quickly, that the propagation of the extended ACL doesn't work that easily. Now, there are a few trick S-bit which allows things to happen, but you have to test that everything works as you expect before you trust it. And all of that is called discretionary access control. So DAC, DAC, by opposition of MAC, mandatory access control, which is a bit more complex, and that you will look on a dedicated lesson significantly later. But if you want to have a quick look at Mac, you can do it. And the DAC side, I gave a link there for introduction to the access control list, which are the extended ACL. Is not Mac. It should be reading DAC DAC on that slide. Sorry for that. So as a conclusion, the Linux boot process, like any operating system, boot is actually complex. The signature is rarely end-to-end. Actually, on embedded device, you have signature end-to-end, which definitely is a very good way to stop people to change that so easily. Doesn't mean they cannot do it. But on a PC, on a server, it's mostly not done. UEFI and Grub, as well as systemd boot, are running on fat partition, and that is a big weakness that requires to have some attention to it. And especially, I told you, standard distribution do a traditional mount of that file system, and that's a bad idea. It should be only mounted by root. That chain is too often ignored, and this is a weak chain. It's a weak point in the chain, and a lot of people ignore it. So please pay attention to it and try to really understand it well. On embedded Linux system, as I told you, it can be signed end-to-end, yes, but it's quite often not better, if not worse. The weaknesses are different, but they do exist in a similar manner. So don't expect it to be any better. Once the kernel is booted, actually you have a very rich set of tools. We only introduce the discretionary access control and the extended ACL, which is really very basic. But you have a very rich set of tools. Now, it doesn't mean that because you have all the tools to look at everything, you will be able to understand what's going on. The dynamic nature of systemd make it potentially very dangerous and risky, and it's a hazardous area. You need to really control very well what you do. Now, as long as you are taking a standard distribution and you use it in a standard way, those people doing this Red Hat and the SUSE and the Ubuntu distributions, they are pretty good, especially the professional version of them. But if you start to play with a non-standard configuration, getting code from distribution or from repo, which are secondary repos or community repos, some are good, some are bad. That means that you will have to qualify it by yourself. And that is definitely an area which requires skills and time. And finally, when you initialize a user session, you can do a lot of more things in the background that quite a lot of people could believe it's possible. So don't ignore that part either. With this, I will invite you to do some homework before you go to the next lesson. So because you have already installed CentOS on your virtual machine, boot it, block the UEFI, and you have to activate UEFI in VirtualBox because by default it's not done. You can write a script to autostart CentOS in your UEFI. You can break it, you can look at what's done and change your kernel config, play a bit with that. Use systemd and autostart Apache, but try to autostart Apache only when a request is coming on the port 80, okay? Which is just a way to check that you have understood systemd. Change your command line in your kernel to boot in single user mode. If you don't know what is single user mode, this is not an admin course, so go on the internet, check what it is. It's fundamental to know how to do that if you have to go on a system which has been attacked. With the ACL, and here I'm talking about the extended ACL, add a default user for read-write Apache welcome pages to understand that, and remove execution access to the command wget and curl to the user running the Apache or the HTTP, light HTTPD web server, whichever web server you have loaded by default. In order to check how it is possible to actually stop the access to a given user to specific command, that's part of the standard functions. And once you've done that, you will be ready for the next lesson. With this, I wish you to have a good time and good fun to play with your system. Bye-bye.